At 8:13 on November 30th, 1942, test pilot Bob Chilton pushed the throttle forward on a silver P-51 prototype sitting on the Inglewood, California runway and felt something he'd never felt before in 19 years of test flying. The Packard V-1653 Merlin engine roared to life with 1,450 horsepower. The aircraft designated XP-51B rolled forward, accelerated down the concrete, and lifted off after just 800 feet of ground roll. In the next 45 minutes, Chilton would discover a problem that should have killed the program. A chemical reaction between dissimilar metals in the cooling system was clogging the radiator. The engine was overheating at combat power settings. Temperature gauges climbed past redline. Any other aircraft would have been grounded immediately. But this wasn't any other aircraft. This was the marriage of the best airframe in America with the best engine in Britain. And that cooling system problem, that seemingly fatal flaw, would accidentally force a redesign that turned the P-51 Mustang into the deadliest long-range fighter of World War II. 23 months later, Lieutenant Colonel Don Blakeslee would prove it over Berlin. The North American P-51 Mustang began as a rejected idea. In April 1940, the British Purchasing Commission approached North American Aviation with a simple request: build Curtiss P-40 Warhawks under license for the Royal Air Force. Britain needed fighters desperately. The Battle of Britain was 4 months away. American production capacity could help fill the gap. North American's chief engineer, Edgar Schmood, had a different proposal. His team could design a completely new fighter in 120 days. Better performance than the P-40. More range. Lower cost. The British were skeptical, but they needed aircraft. They agreed to the gamble. Schmood delivered. The NA-73 prototype flew on October 26, 1940, exactly 117 days after the contract was signed. The British named it Mustang. Initial test flights showed impressive results: 382 miles per hour at 13,000 feet, excellent handling, unprecedented range for a single-engine fighter. But the Mustang had one critical limitation. Its Allison V1710 engine performed beautifully at low altitude, but struggled above 15,000 feet. The single-stage supercharger couldn't compress enough air at high altitude to maintain power. Above 18,000 feet, the Mustang became sluggish, vulnerable, inadequate for the high-altitude combat that dominated European skies. The RAF relegated Mustangs to low-level tactical reconnaissance and ground attack, fast enough to evade German fighters, long-legged enough for deep penetration missions, but not a frontline fighter, not a bomber escort, not the aircraft that could challenge the Luftwaffe over Germany. In April 1942, Wing Commander Ian Campbell Ord invited Ronald Harker, a Rolls-Royce test pilot, to fly a Mustang I at the Air Fighting Development Unit. Harker recognized the airframe's potential immediately. Clean lines, low drag, efficient laminar flow wing. Everything about the Mustang was right except the engine. Harker reported back to Rolls-Royce with a radical suggestion: install a Merlin 61 engine. The Merlin's two-stage, two-speed supercharger could maintain power at 25,000 feet. Combined with the Mustang's low-drag airframe, the performance gains would be extraordinary. Rolls-Royce agreed. They selected 5 Mustang airframes for conversion. The project was designated Mustang X. The first aircraft, serial number AM208, began conversion at Rolls-Royce's Hucknall facility in June 1942. The engineering team faced immediate challenges. The Merlin 61 was 4 inches longer than the Allison V1710, heavier by 180 pounds. The center of gravity shifted forward. The cooling system required complete redesign. Radiator capacity had to increase to handle the Merlin's higher operating temperatures. But the biggest challenge was one nobody anticipated until Bob Chilton's first flight on November 30th, 1942. Chilton climbed to 5,000 feet. The Merlin ran smoothly. Power output was spectacular. He pushed the throttle to combat power, 54 inches of manifold pressure at 2,850 RPM. The Mustang accelerated like nothing he'd flown before. 350 miles per hour in level flight, 380, 400. Then the coolant temperature gauge began climbing. Normal operating temperature for the Merlin was 105 degrees Celsius. Chilton watched the needle reach 110, then 120, then 130. At 135 degrees Celsius, the engine would begin catastrophic damage. Cylinder head warping, piston seizure, connecting rod failure. Chilton chopped power and descended immediately. He landed 22 minutes into the flight. Ground crews opened the cowling. Steam hissed from the radiator overflow. The coolant reservoir was nearly empty. Something was desperately wrong. Engineers drained the cooling system. The radiator core was partially blocked. Green-brown sludge clogged the cooling tubes. Chemical analysis revealed the culprit. Galvanic corrosion between aluminum radiator tubes and brass fittings, accelerated by ethylene glycol coolant. The Allison-powered Mustang had used a simpler cooling system with compatible metals. The Merlin installation required different materials, different fittings, different plumbing. The engineers had focused on fit and function. They hadn't adequately tested chemical compatibility. The failure rate was unacceptable. At combat power settings, the engine overheated in less than 12 minutes. No operational fighter could survive with that limitation. Intercept missions lasted 45 minutes. Bomber escort missions lasted 4 hours. The cooling system had to work flawlessly for extended periods under maximum stress. North America's engineers proposed the obvious solution: replace the radiator with corrosion-resistant materials, redesign the coolant passages, modify the header tank. Simple fixes. Straightforward engineering. But those fixes wouldn't be simple. The Mustang's ventral radiator installation was already optimized for the Allison engine. Changing radiator materials meant changing radiator dimensions. Changing dimensions meant redesigning the entire cooling duct. The scoop beneath the fuselage, the inlet geometry, the exit nozzle, everything would need recalculation. Lead aerodynamicist Edgar Atwood saw an opportunity. If they were redesigning the cooling system anyway, they could improve it. The original Mustang 1 radiator sat close to the fuselage, tucked tightly against the airframe to minimize drag. But that positioning created boundary layer problems. Slow-moving air near the fuselage surface reduced cooling efficiency. Atwood proposed moving the radiator intake forward and down, away from the fuselage. Create a boundary layer splitter. Let the radiator breathe clean, high-velocity air. The change would increase frontal area slightly, adding drag. But improved cooling efficiency would allow a smaller radiator, reducing internal pressure losses. The second P-51B prototype received the redesigned cooling system. New radiator with stainless steel tubes, modified scoop geometry with pronounced boundary layer separation, relocated header tank with improved coolant flow distribution. Test pilot Al Paul flew it on January 13, 1943. He climbed to 20,000 feet and pushed the throttle to maximum continuous power, 50 inches manifold pressure. Coolant temperature stabilized at 105 degrees Celsius. Oil temperature at 70 degrees Celsius. Perfect. Paul held maximum power for 40 minutes. Temperature gauges never moved. The redesigned cooling system worked flawlessly. But the performance improvement shocked everyone. The second prototype was faster than the first despite having the exact same engine. At 25,000 feet, maximum speed increased from 432 miles per hour to 441 miles per hour. 9 miles per hour faster with identical horsepower. Engineers initially assumed measurement error, but repeated tests confirmed the results. The redesigned cooling duct was producing less drag than the original installation, significantly less drag. Enough to offset the increased frontal area and produce a net gain in aerodynamic efficiency. The phenomenon was called the Meredith effect, named after British engineer Frederick Meredith, who'd published theoretical work on radiator duct design in 1936. Air flowing through a properly designed cooling duct could be heated by the radiator, expanded, and exhausted with enough velocity to generate thrust. Not enough thrust to exceed cooling drag completely, but enough to offset a substantial portion of it. The Mustang's redesigned ventral scoop, created accidentally while solving a cooling problem, achieved something close to ideal Meredith effect performance. The boundary layer splitter reduced inlet losses. The radiator heating added energy to the airflow. The exit nozzle accelerated that heated air rearward. The net result was cooling drag approaching zero at high speed. The broken cooling system had forced a redesign that made the Merlin Mustang faster, more efficient, and more capable than anyone had predicted. The accident became the foundation of the most successful fighter aircraft of World War II. Lieutenant Colonel Don Blakeslee hated the Republic P-47 Thunderbolt, 7 tons of radial engine and 50 caliber guns wrapped in a massive airframe, fast in a dive, durable, but heavy, sluggish in turns, and lacking the fingertip responsiveness he'd learned flying Supermarine Spitfires with the RAF Eagle squadrons. Blakeslee had been flying combat since 1941. 3 confirmed kills with the RAF, transfer to the U.S. Army Air Forces in September 1942, when the Eagle squadrons became the 4th Fighter Group. More combat in P-47s, more kills, but the Thunderbolt felt wrong, too big, too clumsy, nothing like the Spitfire he'd loved. In December 1943, Major General William Kepner temporarily assigned Blakeslee to the 354th Fighter Group. They just received the first P-51B Mustangs in the European theater. The 354th needed an experienced leader to introduce the new fighter to combat operations. Blakeslee climbed into a P-51B on December 11, 1943. He started the Packard Merlin. The sound was familiar, identical to the Spitfire's Rolls-Royce engine. He taxied to the runway, advanced the throttle, and felt the Mustang accelerate with authority. The control response was immediate. Light stick forces, precise roll rate. The Mustang felt alive beneath his hands. He climbed to 15,000 feet and flew a series of combat maneuvers, tight turns, barrel rolls, split-S reversals. The fighter responded instantly to every input. Blakeslee returned to base after 90 minutes. He'd found what he'd been searching for since leaving the Spitfire, a fighter that combined firepower, range, performance, and handling in perfect balance. He flew 4 combat missions with the 354th, bomber escort to targets in France and Germany. The Mustang proved everything he'd hoped. At 25,000 feet, it matched the best German fighters, Messerschmitt B F-109s, Focke-Wulf FW-190s. The Mustang could turn with them, climb with them, dive away when needed. Most importantly, it had the range to escort bombers deep into Germany and return to England with fuel remaining. Blakeslee returned to the 4th Fighter Group on January 1, 1944. He was promoted to Group Commander that same day. His first priority was converting the 4th from P-47s to P-51s immediately. General Kepner refused. The bomber offensive was intensifying. The 4th Fighter Group couldn't afford downtime for conversion training. Blakeslee's pilots would need weeks to transition to the new aircraft. Ground crews would need training on the Merlin engine. The logistics were impossible. Blakeslee made a promise. "Give me P-51s and we'll be operational in 24 hours. Kepner didn't believe him. No fighter group had ever converted aircraft types in less than a week. The typical transition process required ground school, familiarization flights, formation practice, gunnery training, tactical exercises. 24 hours was insane. But Blakeslee had an advantage. Most of his pilots had flown Spitfires with the Eagle squadrons. They knew the Merlin engine. They understood British engine management techniques. The P-51 used American instruments and switches, but the fundamentals were identical. Blakeslee's ground crews had worked on Merlins in RAF service. They knew the engine's quirks, coolant mixture ratios, oil pressure requirements, supercharger gear change procedures, maintenance intervals. The Packard V1650 was built in America, but it was fundamentally a Rolls-Royce design. Kepner finally agreed. The first P-51Bs arrived at Debden Airfield on February 13, 1944. Blakeslee watched them taxi in. Silver birds with squared-off canopies and ventral radiator scoops. Beautiful. Lethal. He gathered his pilots that evening. Some had 30 minutes total time in P-51s. Most had never sat in the cockpit. Blakeslee's briefing was direct. You'll learn to fly them on the way to the target. February 28, 1944. The 4th Fighter Group's first operational mission with P-51 Mustangs. 22 aircraft escorting bombers to targets in northern France. The pilots had an average of 40 minutes flying time in their new fighters. Blakeslee led the formation. Everything felt right. Engine temperatures stable. fuel consumption better than expected. The Mustangs cruised at 25,000 feet without straining. P-47s had struggled to reach that altitude. The Merlin's two-stage supercharger made high-altitude operations effortless. German fighters probed the formation but didn't commit to attacks. The mission lasted 2 hours. All aircraft returned safely. Zero mechanical problems. Blakeslee had kept his promise. Operational in 24 hours. But the real test was coming. On March 6, 1944, the 8th Air Force would send bombers to Berlin for the first time in daylight. 660 B-17s and B-24s, the deepest penetration yet. The Luftwaffe would send everything they had. Blakeslee would lead the 4th Fighter Group escort. His call sign was Horseback. The radio chatter that day would make history. March 6, 1944, 0730 hours. RAF Debden, Essex, England. Temperature, 4 degrees Celsius. Overcast sky, 3,000-foot ceiling. Light rain. Blakeslee climbed into P-51 B serial number 436437, his assigned aircraft. No nose art, no kill markings. Blakeslee refused to decorate his fighters. He said it attracted attention. Attention attracted bullets. The Packard Merlin started with the familiar whine of starter engagement, followed by the distinctive thump of cylinders firing. 12 cylinders. Liquid-cooled. 1,380 horsepower at maximum continuous power. The sound that had powered Spitfires, Hurricanes, and Lancasters through 3 years of war. 68 P-51s taxied to the runway. The 4th Fighter Group plus attached squadrons. Their mission, escort B-17 Flying Fortresses to Berlin. The first American fighters over the German capital in daylight. Takeoff at 0810. Blakeslee led the formation into the overcast. They climbed through 8,000 feet of cloud before breaking into clear sky. Sunlight reflected off silver wings. The formation assembled and turned east toward the Channel, crossing the Dutch coast at 0903. Altitude, 27,000 feet. Outside air temperature, minus 40 degrees Celsius. Blakeslee checked his instruments. Coolant temperature, 100 degrees Celsius. Oil temperature, 68 degrees Celsius. Fuel, 170 gallons internal. 2 108-gallon drop tanks full. Enough range to reach Berlin with 45 minutes combat time remaining. The redesigned cooling system that had emerged from Bob Chilton's overheating problem was performing perfectly. At 27,000 feet in sub-zero temperatures, the engine maintained ideal operating temperature without struggle. The boundary layer splitter was feeding clean air to the radiator. The Meredith effect duct was producing thrust nearly equal to cooling drag. Radio call at 0942. Horseback, this is Greenhouse. Bandits at 2 o'clock high. Estimate 40 plus. Blakeslee looked right. Black dots against blue sky. Messerschmitt Bf-109s from Jagdgeschwader 3. They were positioning for an attack on the bomber stream. Horseback to all aircraft. Drop tanks. Prepare to engage. 68 P-51s released their external fuel tanks simultaneously. The aluminum tanks tumbled earthward, glinting in morning sunlight. The Mustangs accelerated. Drag reduced by 30%. Maximum speed increased from 380 miles per hour to 440 miles per hour. The German fighters dove toward the bombers. Standard Luftwaffe tactic. Dive from altitude, attack a single bomber, climb away before escort fighters could react. Fast, violent, effective. Blakeslee rolled his P-51 inverted and pulled through into a diving turn. The Merlin's negative G fuel system kept the engine running smoothly. Earlier Allison engines had cut out during negative G maneuvers. The Merlin never missed a beat. He closed on the lead Bf-109 at 450 miles per hour. Range, 400 yards. The German pilot saw him and broke hard right. Blakeslee followed. The P-51 rolled effortlessly. Control harmony was perfect. Elevator, aileron, and rudder coordination required minimal pilot input. The fighter flew where Blakeslee looked. At 300 yards, he fired. 650 caliber M2 Browning machine guns. 3 in each wing. Combined rate of fire, 4,200 rounds per minute. Tracers reached out. Strikes sparkled on the Bf-109's left wing route. The German fighter rolled inverted, trailing smoke. Blakeslee didn't watch it fall. He was already looking for the next target. Around him, the air battle developed into chaos. P-51s chasing German fighters. German fighters reversing to engage P-51s. Contrails spiraling. Aircraft tumbling. Parachutes blossoming. Captain Don Gentile, Blakeslee's top ace, shot down 3 Bf-109s in 4 minutes. Lieutenant Willard Millikan got 2. The 4th Fighter Group carved through the Luftwaffe formation with precision violence. At 10:15, the bombers reached Berlin. Flak filled the sky, black puffs of 88mm anti-aircraft fire. The bombers held formation and dropped their payloads. Bombs fell toward the German capital, industrial targets, rail yards, aircraft factories. Blakeslee circled above the flak ceiling at 30,000 feet. His fuel gauge showed 90 gallons, enough for the return flight with 20 gallons reserve. The redesigned cooling system and improved aerodynamics gave the P-51 unprecedented fuel efficiency, 3.3 miles per gallon. The P-47 got 1.8 miles per gallon. That difference was the margin between reaching Berlin and turning back at the German border. Return flight was uneventful. German fighters had withdrawn. They'd lost 13 aircraft. The 4th Fighter Group lost 4, 13-4, a ratio that would have been impossible 6 months earlier. Blakeslee landed at Debden at 12:27. He'd been airborne for 4 hours and 17 minutes, most of that time at combat power settings. Coolant temperature had never exceeded redline. The cooling system that had been accidentally optimized during the XP-51B test program had performed flawlessly under maximum operational stress. Ground crews swarmed his aircraft, 71 bullet holes, cannon damage to the left wing, hydraulic fluid leaking. The P-51 had taken punishment and brought Blakeslee home. Liquid-cooled engines were vulnerable to ground fire, but the Mustang's cooling system, redundancy, and robust design made it surprisingly survivable. Blakeslee walked to the debriefing room. Intelligence officers wanted details, tactics, enemy formations. But Blakeslee knew the real story. The first American fighters over Berlin had proven what the redesigned P-51 could achieve. Range enough to escort bombers anywhere in Germany. Performance enough to fight the Luftwaffe on equal terms. Reliability enough to complete 4-hour missions without failure. The glitch that had threatened to kill the Merlin Mustang program had instead created the weapon that would destroy the Luftwaffe. Between March 1944 and May 1945, the 4th Fighter Group destroyed 1,016 German aircraft, more than any other American fighter unit in Europe. Don Blakeslee led the group through the critical months of 1944. He flew 500 combat missions, more than any American fighter pilot in the war. He accumulated 1,000 combat hours. His official score was 15.5 aerial victories. His actual score was probably higher. Blakeslee often broke off pursuit to maintain formation discipline or protect damaged bombers. The P-51 Mustang became the dominant fighter in the European theater. By June 1944, P-51s equipped 14 of the 8th Air Force's 15 fighter groups. The exception was the 56th Fighter Group, which retained P-47s by choice and achieved remarkable success through different tactics. Production numbers tell the story. North American built 15,586 P-51 Mustangs during World War II. More than any other American fighter except the P-47 Thunderbolt. The Mustang served in every theater: Europe, Pacific, China, Burma, India, Mediterranean. It shot down 4,950 German aircraft in air-to-air combat, more than any other Allied fighter type. But the Mustang's greatest achievement wasn't kill ratio, it was strategic impact. Before the P-51, American bombers flew unescorted deep penetration missions and suffered catastrophic losses. August 17, 1943, Schweinfurt-Regensburg raid. 60 B-17s lost from a force of 376. Losses exceeding 15% were unsustainable. After P-51 escort became standard, bomber losses dropped to 3 to 5%. German fighters couldn't effectively attack formations protected by long-range escorts. The Luftwaffe adapted by concentrating attacks at times and places where escort coverage was thin. The Americans responded by increasing P-51 numbers and extending escort range with additional drop tanks. By spring 1944, the air superiority battle had shifted decisively. German fighters avoided combat unless they had overwhelming numerical advantage. Experienced Luftwaffe pilots were being killed faster than training schools could replace them. Aircraft production remained high, but pilot quality declined catastrophically. The cooling system that had accidentally evolved during the XP-51B test program was central to this success. The redesigned ventral scoop with boundary layer splitter gave the P-51 lower cooling drag than any contemporary fighter. That translated directly to range. A P-51D could escort bombers 1,300 miles from base with drop tanks. The P-47N, with enormous internal fuel capacity, could match that range but couldn't match the P-51's efficiency. The P-38 Lightning had similar range but suffered reliability problems in the cold, damp European climate. Engineers continued refining the cooling system throughout production. The P-51D introduced a larger radiator to support increased engine power. The boundary layer splitter geometry was optimized through wind tunnel testing. Exit nozzle angle was adjusted to improve Meredith effect thrust. Each change was incremental. Each change made the fighter more efficient. Modern computational fluid dynamics analysis has confirmed what 1940s engineers discovered through trial and error. The P-51's ventral cooling duct approached theoretical maximum efficiency. Inlet losses were minimal. Radiator pressure drop was acceptable. Exit velocity was optimized for thrust recovery. The total cooling drag at cruise speed was less than 5% of total aircraft drag. Remarkably low for a liquid-cooled installation. That low drag came directly from the problem that had threatened to kill the program. If Bob Chilton's test flight hadn't revealed catastrophic overheating, North American would have used the original radiator design. The cooling system would have worked adequately. The P-51B would have been a good fighter, fast, long-ranged, capable. But it wouldn't have been the best fighter of World War II. The accident forced a redesign. The redesign created unexpected performance gains. Those gains made the Mustang dominant. Decisions made under crisis pressure to solve an immediate problem produced long-term strategic advantage. Don Blakeslee understood this intuitively. In a 1967 interview, he said, "The P-51 was the right airplane at the right time. It had the range we needed, the performance we needed, the reliability we needed. Everything came together, the airframe, the engine, the systems. You could fly it 4 hours at high altitude and bring it home with fuel to spare. That's what won the war." He never knew about the cooling system glitch. He never knew that the ventral scoop beneath his P-51B had been redesigned in crisis to fix a chemical reaction problem. He only knew the fighter worked perfectly, reliably, when it mattered most. Don Blakeslee was grounded in October 1944. General Kepner couldn't afford to lose another experienced group commander after Colonel Hubert Zemke was shot down over Germany. Blakeslee protested. He wanted to stay in combat. But orders were orders. He returned to the United States in November 1944. He hadn't been home in 3.5 years. The war ended 8 months later. Blakeslee stayed in the Air Force. He commanded fighter units in the Korean War. He flew F-84 Thunderjets. Different era, different war, different tactics. He retired in 1965 as a full colonel. He'd spent 25 years in uniform. He settled in Miami, Florida. He rarely gave interviews. He didn't attend air shows or reunions. He preferred privacy. Don Blakeslee died on September 3, 2008. He was 90 years old. 8 days before his 91st birthday, he was buried at Arlington National Cemetery with full military honors. A flyover of 4 P-51 Mustangs in missing man formation passed over the grave. The P-51 Mustang served in frontline combat until 1957, 12 years after World War II ended. It fought in Korea. It served with air forces in 55 countries. Some nations operated Mustangs into the 1980s. The last combat mission was flown by Dominican Air Force P-51s during internal conflicts in 1984. Today, approximately 150 airworthy P-51 Mustangs remain. They appear at air shows worldwide. The sound of the Merlin engine still draws crowds. That distinctive howl at high power, the supercharger whine, the exhaust crackle. The ventral cooling scoop is still there beneath the fuselage. That distinctive boundary layer splitter, the scoop that was accidentally optimized while fixing a chemical reaction problem that nobody anticipated. The detail that made the difference between a good fighter and the best fighter. Bob Chilton, the test pilot who discovered the cooling problem, continued test flying after the war. He flew for North American Aviation until retirement in 1968. He never sought recognition for his role in the P-51 story. He was a test pilot. Finding problems was his job. He found one. Engineers fixed it. The fighter worked. That was enough. Edgar Atwood, the aerodynamicist who redesigned the cooling duct, remained with North American through the 1950s. He worked on the F-86 Sabre, the F-100 Super Sabre, and early supersonic designs. He died in 1962. His obituary mentioned his work on the Mustang in a single paragraph. It didn't mention the cooling system redesign. It didn't mention how an accidental optimization created strategic advantage. The engineers who discovered the chemical reaction problem never received public recognition. Their names don't appear in histories of the P-51. They were working on a prototype aircraft in late 1942. They found a problem, they diagnosed it, they fixed it, they moved on to the next challenge. That's how innovation actually happens in wartime. Not through grand strategic planning, not through systematic research programs, through crisis response, through solving immediate problems with whatever solutions work, through accidents that create unexpected advantages. The P-51 Mustang became the best fighter of World War II because a chemical reaction between dissimilar metals forced a cooling system redesign that accidentally optimized aerodynamic efficiency at exactly the moment when long-range escort fighters became strategically decisive. If you found this story as compelling as we did, please take a moment to like this video. It helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories. Each one matters. Each one deserves to be remembered. And we'd love to hear from you. Leave a comment below telling us where you're watching from. Our community spans from Texas to Tasmania. From veterans to history enthusiasts, you're part of something special here. Thank you for watching and thank you for keeping these stories alive. Claude can make mistakes. Please double-check responses.